In Chapter 13, we will be looking at alcohols and phenols. Ethanol is the alcohol part of alcoholic beverages, and although it's used broadly in lay terminology, it means something slightly different in organic chemistry. So an alcohol is a compound that possesses a hydroxyl group, usually accompanied with a carbon. Although water has an OH group, this does not constitute an alcohol. Ethanol has two carbons with an alcohol. This is cyclopentanol, the cyclopentane with an OH group that is an alcohol as well. Hydroxyl groups are very common in natural compounds. We'll see them in grandisol, which is the sex pheromone of the male boll weevil, in chloramphenicol, which is an antibiotic for streptomyces. It's also potent against typhoid fever. Cholesterol, which you are probably familiar with, which is important in the role of synthesis of steroid in the body. Cholecalciferol regulates calcium levels in our bodies as well. And geraniol has an alcohol group here that's isolated from roses and geraniums, and it is used in the manufacture of perfumes. A phenol is a compound that has a hydroxyl group directly attached to an aromatic ring or a benzene ring. This is just phenol. Many compounds have phenols in them. Dopamine is a neurotransmitter that is deficient in Parkinson's disease, and you can see the phenol outlined in red there. Urushiels are in poison ivy, so there's the phenol compound there. Capsaicin, which is the spicy part of hot chili peppers, if you're into that, there's a phenol compound here along with other parts. And tetrahydrocannabinol, or THC, is the psychoactive drug found in marijuana or cannabis. That again contains that phenol compound. When we name alcohols, this one here, we first name the alkane, which is pentane, and then we tell where the alcohol is and end it in -ol. So the alcohol is on 3, this can be 3-pentanol. Or you can call it pentane. Drop the E, 3-ol. This compound here, the OH is on a carbon chain. This one's a little bit different naming wise because this group here is treated as a substituent. If you determine the stereochemistry, this is R2-chloro, 3-phenyl. So the chlorine is on 2, phenyl is on 3, 1-propanol. This is treated as the carbon chain here. This one we said earlier was cyclopentanol, and this here is R3,3-dimethylcyclopentanol. So in general, the alkanes get the -ol ending for alcohols. When you name phenols, the OH group is attached to the benzene ring, and that is the parent of phenol. This one here, if you name substituents around the ring with phenol here, this is 1. Then we can number this 2, 3, 4. This becomes 4-chloro because we list alphabetically. 2-nitrophenol. If we look at physical properties of alcohols, the OH of an alcohol has a very large effect on its physical properties. If we look at the boiling point of ethane, that's 89 degrees Celsius. If we add a chlorine to that, that increases the boiling point to 12 degrees Celsius because of the difference in electronegativities. If we add an OH group, that increases the number of hydrogen bond interactions. So our boiling point is 78 degrees Celsius. So the boiling point for ethanol is 78 degrees. The boiling point for dimethyl ether is -25 degrees, and for propane is 26 degrees. So these have all similar molecular masses. These two actually have the same formula, but that addition of the OH group having those hydrogen bonds increases the boiling points here. This alcohol is 195 degrees Celsius, and the ether form is 141 degrees Celsius. So when you have these alcohols, it can hydrogen bond, which increases intermolecular reactions. Alcohols also have a hydrophilic region and a hydrophobic region. This is a small difference here because the carbons are so small, but when you have a longer chain, you have a much more pronounced hydrophobic region versus the hydrophilic region. A strong base is usually needed to deprotonate an alcohol. So if you have ethanol with sodium hydride, the hydride portion of the molecule can remove the hydrogen, forming sodium ethoxide and sodium ion. We also get H2 gas evolving. If you have an ethanol with sodium metal, that can produce the same thing. You also get hydrogen gas, but not as much of it. The pKa of an alcohol is between 15 and 18. For the alkane, it's between 45 and 50. For amines, it's between 35 and 40. And for alkyl halides, it's negative 10 to 3. So this is increasing acidity. If you're looking at different factors of acids and bases, you want to remember to compare the conjugate bases of these things. So if you recall all the way back to chapter 2 last semester, we looked at the atom, resonance, induction, and orbitals, and when you were looking at those, you want to compare conjugate bases. And this is the same type of thing. If you have resonance structures with alcohol, more resonance equals something that is more acidic. Cyclohexanol, the pKa is 18. Whereas phenol, which has resonance here, the pKa is 10. So it becomes more acidic with that greater resonance structures here. In induction, can this conjugate base be stabilized by electron withdrawing effects? Ethanol has a pKa of 16. Trichloroethanol with these extra groups here, drawing electron density out, is 12.2. So that makes it more acidic slightly. You also want to look at solvation effects. So can the conjugate base be stabilized by the solvent? So you have a pKa of 16 for ethanol. T-butanol, which is bulkier, has a pKa of 18. So when you add that extra bulk here, the solvent is not as able to get to the alcohol because it is so bulky. So ethoxide here, when you look at the bases, the solvent can access the O- here to help stabilize that. But when you have bulky carbon groups surrounding it, there's not as much solvent that can get in there. So the pKa increases, making it less acidic. We'll look at a practice problem here, just to practice the naming of the compound. So there's a couple of things that we want to look at. We have an alcohol group, so that's going to end in ol. You want to count the number of carbons, and you want the alcohol to have the lowest numbering. So I'm going to have a non-enol. It's an alcohol at 3. I have an ethyl group at 6. And 2 chlorines at 4. I also have stereochemistry here. 1, 2, 3. The hydrogen is in the wrong direction, so this would be S, but it becomes R. So I would have 3R. These are tied here, and then I go out to here, so this becomes 1, 2, 3. The hydrogen is the correct position, so this is R. This is 6R. That is R. So we have 3R, 6R, 4, 4, dichloro, 6 ethyl, 3 non-enol. When you're making alcohols, you can do them either by substitution or addition. If you have an alkyl halide, you can convert it to an OH group, and one of those is using an SN2 reaction, which we've seen previously, using sodium hydroxide, which can do that attack there. We get the OH plus NaCl. If you have a tertiary alkyl halide, you can do an SN1 reaction to form the tertiary alcohol plus HCl. Other reactions we've seen, these are the FGT groups that we've looked at in the last chapter. If you have an alkene, you can make an alcohol using dilute acid. Mercuric acetate. These will both give you the Markovnikov product. This is the anti-Markovnikov product. There's no rearrangement here, but you do have potential for rearrangement here. And then the BH3 gives you the anti-Markovnikov product. You can also actually make alcohols using reduction reactions, so these fall under the reduction category. A reduction, if you recall, is a gain in hydrogens. So if you have a ketone and you're going to gain hydrogens this way, we're going to gain hydrogens across the double bonds. to get this alcohol. And just like we did with H2 platinum nickel, you add hydrogens across the double bond, and you get cyclopentanol. If we were to do the reaction backwards, this would be an oxidation or loss of hydrogen. Hydrogen we've seen reducing an alkene. It can also reduce carbonyls. We have reagents that can donate a hydride that are usually pretty good reducing reagents. One of them is sodium borohydride. That will give you an alcohol 90% yield. And the way that works, we first get a nucleophilic attack. And you have a nucleophilic attack or hug by the H-. So when you have borane making 4 bonds, it's quite unhappy. It's negatively charged. This hydride with its electrons can come in here, or the source of H-, you can think of that. Comes in and attacks this carbon. This is partially positive, partially negative. So this is your electrophile. This is your nucleophile. So you have this extra pair of electrons and the H that got added there. And then the reaction is usually taking place in water or in ethanol, which has a source of protons. So you get a proton transfer. To form the alcohol. So sodium borohydride is a reagent that can do the reduction. We can also use lithium aluminum hydride to do the same thing. This is another source of H-. And we get the OH there. This is 86% yield. Lithium aluminum hydride is more reactive than sodium borohydride. It also reacts violently with water. This works in a very similar mechanism. You have the H-, which acts as your nucleophile. That's going to attack this electrophile. Those electrons go up. And then you get a proton transfer. To form the alcohol. So hydride delivery is specific to carbonyl compounds. If you had sodium borohydride with methanol, that will reduce the carbonyl to an alcohol. This is 90 to 95% yield. Sodium borohydride methanol or the lithium aluminum hydride plus water will give you this alcohol. If you use H2 platinum palladium or nickel to do this, that's going to reduce the carbonyl as well as the alkene. So you would end up with cycloheptanol, and that would work in 90 to 95% yield as well. So if you want to reduce both of the double bonds, you can use hydrogen. If you want to selectively reduce just the carbonyl, you want to use sodium borohydride or lithium. So you can go ahead and try these practice problems here. Sodium borohydride with a carbonyl will get the alcohol. Sodium borohydride with this carbonyl, again you get the alcohol. And same thing here with sodium borohydride, we get the alcohol. With these reactions you get a racemic mix. So the hydride can attack either face of that carbonyl. You can also make alcohols via reduction with different functional groups. So here we saw carbonyls and aldehydes. We can reduce carboxylic acids and esters as well. You would need to use excess lithium aluminum hydride. Sodium borohydride does not work with carboxylic acids and esters. So in this case, when you reduce, you're going to get this plus the alcohol. So lithium aluminum hydride is strong enough to reduce esters and carboxylic acids, whereas sodium borohydride is generally not strong enough. And I'm sure you're dying to know how this reaction works. You have delivery of a hydride, as we've seen before. This is your nucleophilic hug. In this case, we have a leaving group that's attached to the carbon. So we're going to get a loss of leaving group. And that will be motivated by this reforming that carbonyl bond because it can. And that will kick that leaving group off. So the reformation of the carbonyl is a driving force there. And then we have this aldehyde that forms. And so if you recall on the last slide there, we had the excess of that. So this is the aldehyde that we formed here. They're going to have another hydride reacting. So that excess is going to reduce it because lithium aluminum hydride is strong enough for aldehydes as well. Get a proton transfer. And that proton transfer. So again, you need excess. So this methanol that was kicked off up here is not seen, but we have OMe minus, which can pick up a proton later. If you add sodium borohydride to this reagent, that will reduce the carbonyl only, but not the ester, which is seen here. So you get just the OH. But if you now use lithium aluminum hydride, that will then reduce the ester. That double bond stays there. And the thing that happens with this, the oxygen that was here left, so that's a leaving group. And that will get protonated, and this just becomes an open ring here. You could also do this reaction using LaH excess followed by acid or water. If you want to reduce both of these, carbonyl and the alkene, this is when you can use H2 nickel. If you just want to reduce the carbonyl, then you can use NaBH4. If we're looking at naming diols, it's named just like alcohols, except we use the suffix diol. So in this case, we have 3 carbons. This is 1,3-propane diol. This would be 1,5-hexane diol. To make a diol, using the methods that we'd seen previously, you can use H2 palladium, lithium aluminum hydride, sodium borohydride. Those would all be reagents that you could use to get the diol. To make an antidiol, again, what you've seen in chapter 9, you can use a peroxide with the addition of acid and water to get you the antidiol. And then you make the syndiol using osmium tetroxide. Those are reactions you've seen already to make a diol. Reactions that we haven't used yet to make alcohols include a Grignard reaction. A Grignard reaction is made from an alkyl halide with magnesium. The Grignards are reagents that are often used in the synthesis of alcohols. So when you add magnesium to an alkyl halide, it will insert itself in between there. If you look at the electronegativity of Rx, this is partially positive, partially negative. When you put that magnesium in there, that kind of flip-flops the things, makes this partially negative. This is the partially positive. This is partially negative. So that magnesium inserts itself and the carbon becomes nucleophilic. So this is called Umpelung, where you switch polarities. So this alkyl halide, the carbon goes from being partially positive, we insert that magnesium, and then it becomes negative. The electronegativity difference between carbon, which is 2.5, and magnesium, 1.3, has enough bonding character that this becomes ionic. That carbon atom is not very good at stabilizing the negative charge, so it makes it very reactive. So magnesium with this bromobenzene will insert itself into the benzene. So this is now a partially negative carbon, partially positive magnesium. And it can insert itself in between here. And this is again partially negative. So as you can see here, this partially negative here, partially negative carbon on the benzene plus the magnesium bromide is partially positive, which is the equivalent of having this carbon be negative. So once we make a Grignard reagent, and this is the Grignard reagent here with that magnesium between the carbon and the halogen, we can use it to attack a carbonyl. So that R, which is the Grignard, this is your nucleophile. That's the electrophile. We'll attack here. Those electrons pop up. And then we add a new carbon. So this is a carbon-carbon bond forming group, as well as it's going to create the alcohol. And those electrons are up there. And this is a nucleophilic hug. So that Grignard again is our nucleophile with that R- that was created. That hugs the electrophile. Those electrons go up top. This is now nucleophilic. These reactions are usually followed by water, so we can do a proton transfer. And the R nucleophile does not need to be the same as these other R groups here. It can be something else. So this could be an R1, so that it makes a new tertiary alcohol. And that is the mechanism of how the Grignard works. So this is a reaction that falls into the reduction category because we're going from carbonyl to alcohol, and we're also doing a carbon-carbon bond forming reaction. So that one can actually go into both categories. So if we look at this problem here, we have a CH3MgBr. This is our Grignard reaction. This is the nucleophilic carbon that's going to get added. That will attack here. So your product at the end of the day, we form the alcohol, and we're also going to add CH3 there. This is what would happen with a ketone if you had an aldehyde with a methyl Grignard, followed by water. We would add that methyl group and do this as well. So with a ketone or an aldehyde, we're going to get an alcohol, and the degree of alcohol depends on what you started with. So a ketone will give you a tertiary alcohol, and the aldehyde gives you the secondary. Grignards can also work on esters if you have an excess of that. When you have an excess of Grignard reagent with an ester, we're going to end up with a tertiary alcohol by way of addition of 2 Grignards here, plus methanol. And the methanol came from that right there. And the way that this works, your Grignard is acting as the nucleophile, so we're going to have that nucleophilic hug, the electrophile here. So we add 1 methyl group. And at this point, the oxygen can look to either pick up a proton, or if it can reform a carbonyl, it will. So that is the driving force here, is to reform the carbonyl by losing this leaving group. So this is our loss of leaving group. This was a nucleophilic hug. We reform the carbonyl, and carbonyls or ketones are reactive to Grignards, and there's more of that around. We get that addition of the second methyl group. And there's water that can protonate that one, proton transfer. Ester with excess Grignard, this will give you tertiary alcohol. This is a cyclic ester with Grignard. This is the nucleophilic carbon right there. So this product I have in O. I'm going to add 2 Grignards to this carbon, just to make sure I got all my ducks in a row here. So this is 1, 2, 3, 4, 5. This is going to be the leaving group here, this O group. That will get protonated. This will get protonated. I'm going to add a CH2 with the ring here. I'm going to do that twice on there. So that would be the product there. You could also abbreviate these rings with pH, which stands for phenol. So the Grignard can act as a strong nucleophile, which we've seen. It can also act as a strong base. If you add a Grignard reagent to water, it will immediately grab that hydrogen from the water and then reform the alkane. This has a pKa of about 15.6. This pKa is around 50, and then we get HOMgX. So you do not want to do Grignard reactions in water. You also don't want to use Grignard reactions if you have an alcohol in the same molecule. So in this reaction, if you had an alcohol here and you wanted to form a Grignard, these are not compatible. This would deprotonate here, so that would not be a good idea to use that. Because Grignards can act as a base, these do not work well with carboxylic acids. You just get acid-base chemistry. So this Grignard reaction with a carboxylic acid will grab this proton, and then you form the carboxylate here. So we can look at a couple of practice problems here. The first one, we have a ketone. This is the Grignard because it has the MgBr. These are all Grignards. We add the methyl group and the OH. Methyl group and the OH. We have excess MgBr here because we have an ester. So we're going to add 2 methyl groups and make this an alcohol. So the Grignard can be any carbon group. It doesn't have to be methyl, as we saw with the phenyl groups there. So if you're looking at synthesis problems, how would you make this? We have a tertiary alcohol. So there's a couple of different ways that you could make things. And any of these things can have come from a carbonyl. And I'll show you the different ways that we have here. So I'm just going to abbreviate this pH here just to kind of save writing. Option 1, you could start with the phenyl. So if we start with this, you can see that would be this part of the molecule here. That carbon right there is what would have to be attacked. And because we're making an alcohol and using a Grignard, we knew that we had to have a carbonyl compound here beforehand. So if I'm using this particular ketone, I'm going to use a Grignard. This is only 1 carbon. That's only 1 carbon, so I'll use CH3 MgBr here, and that will get us the correct molecule. Another approach you can take is, outline this here. This could be the starting material there, so that would be method 2. And in that case, this ethyl group is being added, so I'm going to add ethyl MgBr followed by water, and that will get me the same thing as well. The last thing that you can do is to use this part, and this is getting kind of craggy here, you can use that part of the molecule as the ketone. So I would have a ketone here. This is 1, 2, 3, 4. And then you're adding the pH MgBr with H2O. So all of these methods will give you that Grignard. So you can try to design a synthesis for each of the following molecules, starting from an alkyl halide and also a carbonyl that has 5 or less carbon atoms. And so with the alkyl halide, that means that you will have to make a Grignard reagent with the alkyl halide. So if we're looking at different strategies here, I have, let's see, 1, 2, 3, 4, 5. This has a group of 5 carbons here. 1, 2, 3, 4, 5. I can't make one using the chain straight across. That has 6 carbons. What I do notice, though, I can do 5 carbons here in this string here, 1, 2, 3, 4, 5, and you could use this as a group. So there's going to be a couple of different ways that you can do this one as well. If I use this as my ketone, I would have to make a Grignard out of that. And that's really just taking this molecule and slapping a Br on it, adding magnesium. And then we can add that to the reaction. So that would be one method. All right, for this one I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This one has a couple of solutions. So, but if I just do one and I use that as the carbonyl, one, 2, 3, 4, 5. I have 1, 2, 3, 4. Alkyl halide. I add magnesium. So once I've made that, I can use that in my reaction. And that will get me to the target molecule.